Okay, good morning. Let's start the class. So today we will continue the discussion on sets. And then we will first describe a bunch of concepts. So first of all, we will introduce what is subset. And then we will talk about some set operations that allow us to create new sets from old sets. So we have some old sets, and then we have some operations so that we can create a new one. It is just like we can use the plus, add, to add two numbers, right? You can have 1 plus 2. You create a new number 3 based on this 1 plus 2. So similarly, we will have some set operations that allow us to create new sets. And after that, we will talk about identities. So sometimes you can, so it is like the proposition that we have. So for proposition, we have propositional identities, right? So equivalence. So here we will have something like that. Okay, so everything here should be simple. So let's talk about subset. Okay, so let's have a set A. Let's consider A. Let's say A contains, there is a sun here, there is a moon here, and there is a star here. So this is A. Okay, and let's consider another set B. Let's say B is just the sun and the moon. So in this example, we see that everything that appears in B also appears in A. Is that okay? So it is the case that B, everything in B is included in A. In this case, we will say B is a set, and then B is a subset of A. Okay? And then we will write, so for shorthand notation, we will write down something like this. B, a symbol of this one, A. Is that okay? B is a subset of A. So if you are interested, so we can also call A is a superset of B. Okay? And then in that sense, we will also sometimes we write A something like this. So A can contain everything of B. So A is a superset of B, and B is a subset of A. Is that okay? Okay. Now, let's take a look of another example. This time, let's take a look of a set C. So let's say C contains number 1, 2, 3. And then D. D also contains number 1, 2, 3. Is that okay? Is that okay? So everything in C appears in D. So we can write C is a subset of D. Is that okay? But on the other hand, you see that everything that appears in D also appears in C. So you can also write D is a subset of C. Now with these two together, everything in C appears in D. On the other hand, everything appears in D, it will appear in C. What does it mean? It means that the two sets contain the same items, right? Anything here appears there. Anything there appears here, right? So that's the case that we will say the two sets are exactly the same, and we write C is equal to D. Is that okay? Okay, very simple, right? Now, this is a tricky case. Okay, so this is a tricky case. Okay, let's have a set E. So E is an empty set. It doesn't contain anything. And let's say we have an F. F is a set that contains the English character A. Is that okay? Okay. Now, E does not contain anything. So it is still true if I say anything appears in E appears in F. Does that make sense? If something is in E, then that thing is in F. This is going to be a true statement. Okay? So in this case, we still write E is a subset of F. Is that okay? So in general, any empty set, this is the empty set, any empty set is a subset of some set S. And then empty set is also defined to be a subset of itself. Is that okay? So this is very strange, but this is the boundary condition. Okay, we define this. We will say empty set is also a subset of the empty set. Okay. Now, how about this one? Okay. Let's have another two sets. This time we have a G. Let's say G contains 1, 3, 5. Okay, let's say H. This time it contains 1, 4, 7. Is that okay? Then in this case, we see that it is not true that everything in G appears in H. Not true, because you can. There is a 3 inside G, but there is no 3 inside H. So we write down G is not a subset of H. And for here, it is also true that H is not a subset of G. Okay? This is it. So this is all the things that you need to know about this subset. Okay? So one set can be a subset of the other if everything inside the first one appears in the second one. And then we can use subset to show that, okay, this is the case, to show that two sets are exactly the same. We just need to find out one set is the subset of the other and the opposite, the vice versa. Okay? And sometimes, for any two sets, it is not true that one is always a subset of the other. So in this case, neither is a subset of the other set. Okay, that's it. That's we need to know. Okay, and now let's talk about set operations. Okay, so the first one is we have the union operation. So we are talking about set operation, the union operation. So I have a set A, and then I have a set B. Okay, the union of A and B, we can write it down like this. It is a set that contains everything that is in A or in B. All items of A or B. Is that okay? So let's take a look of our example. So let's take a look of G and H. Okay. So for this G and H, we can define the. So we define the union of these two, G union H. It is equal to a set that contains everything that is in G or in H. So you will have 1, you will have 3, you will have 5. So these are the things that is in G. You will also have 4, and you will also have 7. Is that okay? So this is G union H. Is that okay? And then this is also the same if you write it as H union G. Is that okay? Yeah, so the ordering of union of two things doesn't matter. Okay? So the critical thing here is or. Okay? And this is easy to remember because it is called the union operation. Union means join. You join things together. So it is a U symbol. And then we can define another set. Okay, so you have A, you have B. We can create a new set. I call it A and B. So this is intersect. So this is the other operation is called the intersection operation. So the intersection operation, this is A intersect B, is a set that contains all, okay, common this time, items of A and B. So this is the AND operation. So here, this time, we can only pick up common items. So if things only appears in exactly one of the sets, then we don't include it. So in our example, so let's say this is G and this is H. So we will have G intersect H. It is equal to what? So the intersection of G and H, it turns out that it is equal to a set that contains the number 1 inside. Is that okay? Is that okay? Okay. How about this case? How about this case? We have E is an empty set. We have F is a set that contains the character A. So what is the intersection of these two sets? So what should be included? So you have nothing. Very good, nothing. We should include nothing. So if one of the set is empty and the other set is whatever set that you have, then the intersection will be empty. Is that okay? But sometimes you don't need to have empty intersect something to get empty. Let's create a new set. Let's call it H prime. So let's say this H prime is you contain 2, 4, 6. Is that okay? Now you have G here, you have H here. The intersection of these two sets will still be empty because anything here does not appear here, and anything here does not appear here. Is that okay? So their intersection is still empty. Okay, and then if this happens, then we say these two sets are. So we have an adjective to describe them. They don't have anything in common, so we call them disjoint. Disjoint. So the two sets G and H prime, they are disjoint because their intersection is empty. They don't have anything in common. They cannot join. Yeah, they don't have anything in common. Disjoint. Okay? And then another one. We will also define something called the complement of a set. So the complement of a single set, you have an A, and then you write a bar over it. So it is a set that contains anything, okay, or everything, all the things. So the anything so any interested thing, I will call it. Anything interested that is not inside this A. Is that okay? So what is meant by interesting? Okay, so you have a set 1, 2, 3. Okay, so let's call it A. Then what is the complement of A? Okay, it depends on what you are talking about. So if you are talking about, we are only interested in the integers from 1 to 10. Okay, then what? Then the complement of A will contain the numbers 4, 5, 6, 7, 8, 9, 10. Is that okay? Or on the other day, if you say that we are interested in all the integers, positive, negative, or whatever, then in that case, the complement of A will include 0, minus 1, minus 2, up to minus infinity, 4, 5, 6, up to infinity. Is that okay? And then maybe on another day, you may think of things that are interesting, like we think of all the real numbers. Then in that case, it will include even more things. So you will have numbers like 1.1, 1.2, 1.3, and 1.111, and so on and so forth. As long as it is a real number and it is not equal to 1 or 2 or 3, it should be included. Is that okay? So in that sense, we will call something called the universe. So we will have a concept of universe. The universe is, it represents all items that are interesting. Okay. all the items that are interesting, all the items that we want to discuss. So in order to define what is the complement of a set A, then we need to define what is the universe at the beginning. So once you have the universe, you can define what is the complement. Is that okay? So it is like the domain. When we talk about predicate calculus or the quantifiers, so you have for every x. So what is meant by for every x? X can be a pig, a sun, a moon, a boy, a girl, a number 1, a number 2, right? We need to define what we are interested. This is the domain that we are talking about. So it has the same concept. The universe for a set are all the items that we are talking about. So A, you can say that it is all items. So A, the complement of a set A with respect to a universe U. So the complement of A with respect to the universe U is all items in U that is not inside this A. So this is what we want. This is the exact definition. Okay? Is that okay? Good. So we have complements. And then there are two more that I want to introduce. So we can also talk about the difference. And we will talk about the power set. But before we talk about these two things, let us take a look of an excellent way to represent the relationship of this A, B, A union B, A intersect B by a diagram, the Venn diagram. So we have talked about this Venn diagram when we are talking about this counting. Okay? And then what is the Venn diagram? So a Venn diagram is a diagram to represent the relationship between the sets. Okay? So it is usually drawn in a box. This box represents the universe U that we are interested. Okay, so we use these geometric objects like a circle, an ellipse or oval, or you can, if you like, a small rectangle as well, or you can use whatever, like a triangle to represent some set. So I can write down A is a set like this. Is that okay? So it means that everything that is circled inside A will be contained in A. So imagine this representation, it means that, okay, in this universe, it is full of items. So each item, you can think of this as a small dot, and then there are some dots inside A. So A will contain all the items represented by the dots. So for instance, in our this example, A is 1, 2, 3. So it contains an item 1, it contains an item 2, and it contains an item 3. Is that okay? Okay. And then if, let's say, the universe, we define it to be all integers, then in that sense, you will see that, oh, there can be some number 4 here, there can be some number 10 here, there can be some number -1 here, there can be some number -7 here, and so on and so forth. We don't need to draw them more, but these are some examples that we can draw. Okay? Okay? Now, in that sense, if this part represents A, then we can use this orange color to shade this part. So the orange part will be what? It will contain all the items that is exactly not in A. Am I correct? So in this sense, the shaded part will be the complement of A. Is that okay? Good. So the shaded area, it is equal to the complement of A. Okay? Okay, now using this Venn diagram, we can also talk about the union. So let's say this is A, okay? And let's say this is B. So in general, we draw two circles like this because there may be some chance that there's some common, so all these parts are common items that appears in both A and B. And this is a part that there are some items that is in B only, but not in A. There are some items that may be in A only, but not in B. Is that okay? So this is, in general, we draw two circles intersecting each other. Now in that sense, if you shade the part here, then this will represent what? So the shaded part, it will be representing A what? Union B. Is that okay? So we have A union B. And now we can also have, so let's have another one. So let's say this is A, and let's say this is B. So how do we get A? So I want to, this time, let's try to get A intersect B. So I want the shaded part to represent A intersect B. So what should I do? So I should shade this area. Is that okay? Is that okay? So this area represents the case that items are in both A and B. Okay? Now difference. So what is the difference? Set difference. Okay, so let's use this side. So the set difference will be like this. So let me draw it, and then you will understand what it is. Let's say this is A, and let's say this is B. Okay. And then the set difference, you can say something like A minus B is this part. Is that okay? This is called A minus B. So you get A, but you take away anything that is in B. So you have A at the beginning. So these are the items that you can get. But then if you find out some items inside are also in B, you take it out. So this is A minus B. Is that okay? Okay. So using the Venn diagram, you can see that. So what is A minus B? A minus B can actually be represented using union, intersection, or complement. So so how do we get? So let's take a look. Okay. So I'm claiming that you can, so A minus B is exactly equal to, it is exactly equal to, always equal to, you take A at the beginning, and then you union, no, not union, you intersect the complements of B. Well, this looks very complicated, but let's see. Okay. So what is, so let's draw this again. So this part, this is A. So A is easy, right? The complement of B is difficult to visualize. But let's take a look of where is the complement of B. So let me shade it in what color? Let's try. So where is complement of B? So this is complement of B. Is that okay? So the green part is the complement of B. And where is A? A is this part. Is that okay? And then to get A intersect complement of B, we need to find a region such that it has both colors. It has the green color because it is inside complement of B, and it has the orange color because it is inside what? It is inside A. So in that sense, we will have this area. This is the only part. This is the only part. that contains both colors. So using the Venn diagram, you see that this is exactly the case. So A minus B is exactly equal to A intersect the complement of B. So why we want to define an operation like this? Because this is more straightforward. Okay, it looks like our daily operation of minus. You have A and then take away things. Okay, so this is easier to visualize, and this is difficult, but they are equivalent. And this is the so-called identities. So we are showing that there are two ways to express the same thing. This one is always, for no matter what A and B you talk about, this is always equal to A intersects not the complements of B. Okay, we will talk about more about identities later. Okay, so this is difference. And now, the last concept here, the power set. Power set is something perhaps new to you. So the power set of A. So you have an A. So I write down the power set. So power set is difficult to use Venn diagram to represent. It is another concept. The power set of A is a set. So it's a set. So it is still a set. Okay, such that it contains every subset of A as its element. Okay, so the power set of a set A, it is still a set, but then inside the set, it is not just plain item. The element of this set will be the subset of A, and it contains every possible subset of A. So I'll give you an example.